Okay, today is September 28th, and this is our third lecture, I think, on map estimation. It's ECE641, model-based image processing, and so I want to, okay, whatever. Here's the thing, map estimation, x hat equals arg, there's not enough, like the university theoretically has an official designation of who's online, who's not, but that's kind of bogus. I think it's individual choice. This, okay, and then this is log p of y given x, log of p of x, okay? So everybody's got this, right? Yes.
Doing the negative log, shouldn't we be argmin now?
Yeah. Argmin, yes. That's correct. So that's the solution you're looking for, okay? That's the map estimate. And in the particular case where y equals ax plus w, then this x hat works out to be where this thing, x here is n 0, say Rx, and this thing is N0 RW, okay? Then this thing is the arg min over x of 1/2 the norm of, oh, I think we made this lambda inverse, okay? Okay, y minus ax squared lambda plus 1/2 x transpose bx, where Rx here is b inverse. So Rx is equal to b inverse, and Rw is equal to lambda inverse, okay? So lambda and b are the precision matrices, and Rx and Rw are the covariance matrices, right? And then if you solve the equation, you get that x hat is equal to A transpose A plus sigma squared B inverse A transpose times Y, right? And so you'd say, well, okay, I'm done. But that's not very practical because you can't really compute this. This is not practical. So the general thinking is that closed form solutions are good, right? And that's a closed form solution, but it's not good because you really can't compute it because the matrices are way too big, and it's like really ridiculous because this thing, if you have 1,000,000 pixels, this matrix is 1,000,000 by 1,000,000. And when you go to invert it, inversion is order n. I think inversion is order n cubed, if that's correct, okay? Where n is so this would be 1,000,000 cubed complexity. So that's just ridiculous. I mean, that's not going to happen. Billion, that would be 10 to the 18th. So a teraflop is, a tera is 10 to the 12, right? So 10 to the 12 into 10 to the 18 is 6. So it would be 1,000,000 teraflops. So it would be 1,000,000 seconds, just if it was one operation per whatever, okay? And 1,000,000 seconds is what? It's a long time, okay? I'm pretty sure 1,000,000 seconds is about 30 years. Is that correct? No, it's 1,000,000,000 seconds is 30 years? Okay, it's a long time, and even that would be a wild underestimate, and that would be just not interesting. Yeah?
Isn't A triplets block triplets?
Yes.
So couldn't we simplify that calculation by using a convolution?
Well, it needs to be circulant.
Okay. Isn't that the assumption that we're dealing with?
Toplets doesn't mean circulant.
Okay.
So you're on the right track. I'm not disputing your logic. I'm just refining it, okay? That toplets isn't good enough. You need circulant. So the difference being just the boundaries, okay? But A is not, A would be circulant in the case when, say the forward model is a linear space invariant filter. Then it's circulant. But in lots of cases, it's not circulant. But even if A is circulant, B isn't circulant usually. Well, it might be. Actually, I'm kind of, like, okay. I'm sort of being a hypocrite here because I've been telling you about the circulant case, and then I'm saying it's not circulant. It could be, it's going to turn out that the circulant case is interesting, but not terribly interesting because it's not practical, because it's really terrible. I mean, it's a lousy model because then you're assuming the thing's Gaussian, space invariant. You can do that. It has some value in certain applications, but it's not a very good image model, okay? But we'll learn that in a bit. But you're right. In that case, you could do this all with FFTs, and then it is practical, okay? You can do it, basically, you can compute the solution in closed form. I actually added a homework problem in one of the sections, one of the chapters, on exactly that problem, because it came up recently with a student, and I thought, oh, this is something that the student should know how to do. So you're absolutely correct, okay? Okay, but the problem is it's not terribly useful. Okay, that's a very restrictive case, so it's not really useful. It's not broad, it's useful, but it's not broadly useful. That's a better way of putting it. So, yeah, you can do that, but let's assume you're not going to. And so then you come back to this thing. You want to do direct optimization of this. So, and the reason, so the direct optimization works in more general cases. But we'll actually consider for the less general case because it's easier to think about. And then we'll show how to do the more complicated non-general case, less general cases of circular matrices. By the way, if A here is in tomography, which is a problem near and dear to my heart, in tomography you have something like this, right? And then you have the projections of the object. Do people know what tomography is? Is there somebody who doesn't know what tomography is? It's when you take projections to an object. That's what happens in like a CT scanner, okay? So in this case, A is not circulant. But it turns out that A transpose A is approximately circulant, okay? Oh, by the way, here's another bug in the ointment, you might say. Actually, what I wrote there was incorrect. It's really this. And then you can't do it with FFTs. You could do it with an FFT if A is circulant, but you can't do it with an FFT if A transpose A is circulant. So in tomography, A transpose A is approximately circulant, but not exactly circulant. And usually you want these things to be pretty accurate because if you start making big approximations, you degrade the quality of solution enough that it's not even worth all the extra trouble, okay? So, okay, so the strategy is going to be to do optimization. Now, the most canonical type of optimization is what's called gradient descent. So most optimization algorithms have the following form, okay? They say until converged, where you initialize x, okay? Then what you do is this, you say, okay, you have some algorithm, you say like find direction. So this thing returns a direction d, okay? And in order to find the direction, you need to know the function you're minimizing. So f of x then is equal to 1/2 norm of y minus ax. We'll leave out the lambda just to simplify things a little bit. But the lambda is actually important in practice because it tells you which measurements are more reliable. Plus 1/2 x transpose bx. Okay? So our goal is to minimize this. So this function, this direction function needs to know f, okay? Right? It needs to be, it knows to know the function actually, not just its value at some point. And it needs to know x. You know, so somehow you have some kind of method for finding a direction. Then what you do, then you do a line search. You do arg min over alpha, say greater than 0 of f of x plus alpha d, and that yields alpha, we'll call it, I don't know, I'll call it alpha star, okay, because it's the best value of alpha. And then what you do is you take x and you update it by moving a direction star, alpha star, in direction d, and you repeat. I mean, most optimization algorithms have this general structure. There's other things you can do where you just, maybe things where you like bounce around or whatever. But most algorithms, most commonly used optimization algorithms have this structure. So it really comes down to finding a direction and minimizing along that direction, and then you repeat. It's like wash, rinse, repeat kind of a thing, okay? So it turns out that, and also there might be constraints in here. Like sometimes you have a thing called a positivity constraint, which is a little bit of a misnomer. A positivity constraint really means a non-negativity constraint, okay? But it's easier saying positivity than non-negativity, and everybody knows what you mean. So you don't want pixels to go negative. And that may be for physical reasons. Like in the CT example, what you're reconstructing is the absorption of a voxel. So a voxel, under normal conditions, a voxel can't have negative absorption. In other words, it can't generate energy. I mean, obviously, there could be counterexamples to that. It turns out that there's actually some fairly common counterexamples in certain cases. But in a lot of cases where you have passive materials and so forth, the voxels have to be positive. Another example would be if you have a photograph, you know that the light coming from a point in the image can't be negative. That doesn't mean, oddly, you can get negative values because there's things like dark current in sensors, and when you subtract it off, you can actually get negative values. Another example, there's a thing called emission tomography, which is similar to conventional CT. So there it's more like there's a thing called a SPECT, single photon emission tomography, you know that, and gamma cameras measure emission rates along lines. So in that case, the values should be positive, but you get background radiation and so forth. So when you subtract it off, you can actually get negative values. So, but in any case, there are constraints like positivity that can be useful. Okay, so what ends up happening is that there tends to be a trade-off between these two things. Oh, okay, so, but I'll tell you, the line search. So the line search, this thing is called the line search. A line search is going to be a very important concept. Doing the line search efficiently is one of the more challenging things, okay? So that's kind of a unit of computation, you might say. And if you can do that efficiently, then it changes the trade-offs. There's some algorithms, finding the direction is really simple. But then there's different trade-offs, okay? In some algorithms, finding the direction is expensive. But then once you find the direction, the line search might be easy or something, okay? In other algorithms, you know, the trade-off may be different. We're actually going to look at basically just two algorithms, because honestly, they kind of represent the canonical examples of a large class of algorithms. We're going to look at gradient descent, okay, and then I'm going to look at coordinate descent. In gradient descent, finding the direction is computationally relatively expensive because you have to compute the gradient. Then with the line search, you have a choice. You can try to do the line search very accurately, or you can try to do it very badly. The simplest thing to do is just to make alpha constant. So you just skip this step. Then you have gradient descent. So you have the advantage that you save this step, but the disadvantage that you have to end up doing more line searches, okay? And these update, of course, too, but that's not usually so bad. This is usually pretty fast, relatively speaking. So gradient descent is simple. Then the next more complicated thing is steepest descent, where in steepest descent what you do is you pick the alpha so that it's the best alpha. So, so this is going to be the function. So this is alpha, and that's going to be alpha star, okay? Notice that the value of the cost usually you pick the direction so that you at least start off by going down. Because it would be a really bad idea to pick a direction that starts off by going up, okay? Generally speaking. But then now you say, well, I just picked this value here. That's the line search. You find the value that minimizes this. It seems like very simple, right? So what would you do? Well, usually what happens is that you have some function f, and there's some computational cost associated with evaluating f. So for instance, over here, what you'd have to do is you have your measurements. This is an image. You apply this operator. You subtract them. You square it. Then you have to do this thing. This is like a local operation in the image. It's like applying a filter and then multiplying by the image. So, but evaluating this is, you know, not cheap. You have to at least touch every pixel in the image. And usually you have to do quite a bit more than that. If it's tomography, then this forward projector is expensive. So the problem is you have this curve in concept, but in MATLAB, you just like plot this curve out and you'd take the minimum, right? By the way, there's a universal constant. I'm pretty sure if they find alien life forms, the alien life forms will use the same number, okay? Which is the number of points you use when you do a MATLAB plot. It's exactly what number? 100. Every person always uses 100. Why? Because 10 is not enough and 1,000 is too much. Sort of. So if you did this 100 times, that would be 100 times the computation of doing this once. That's very expensive, right? So you don't really have this curve. Now what you could try to do is say, oh, well, I'll try to poke around like in the dark. Has anybody ever played the game Battleship? where you try to poke around and find the minimum, right? There are different algorithms for that. One of them is called golden section search. That's sort of the most common. But that's slow too. There's an algorithm, I think I have you do it in the labs. If you can compute usually, often, so this thing here is f, okay? It's not really f, f is a function of alpha, because it's a one-dimensional. The way to think about this is it's like you have this high-dimensional space, and you're taking a slice through it, right? You're looking at the value of the function along a straight line, okay? So you could also plot the derivative. So this would be x plus alpha d. You could plot the derivative, so then that would be f of x plus alpha d d alpha. And that happens to be equal to, you can compute that derivative, right? At least partially. It turns out that that's equal to, you took the gradient of f at x plus d, plus alpha d. And that times an inner product with E sub, times the inner product with D. And that's the same thing, right? So basically, computing this derivative with respect to alpha requires that you compute a gradient of f. Computing the gradient of f is computationally expensive too. If I compute the gradient of f, it looks like this. People, if you don't know, I'm going to use like standard matrix algebra results, okay? If you're not familiar with them, go look them up or rederive them from first principles. But this is going to look like, it looks like y minus ax transpose times minus a, okay? And then plus x transpose b. That's what that's going to look like. So I could rewrite that if I take the transpose. You can. In this book, I usually write a gradient as a column vector. If you really want to be a purist, it should be a row vector. But I picked a method that was notationally simplest. Do you have a question?
So when you're writing out the gradient, are we ignoring? We shouldn't be ignoring the cap lambda, should we? Because I feel like that.
No. Yes. Well, only because for purposes of keeping things simple, I'm setting it to I.
Okay.
Okay. But yes, you should go through the same calculations with the lambda in there, because that's the case that actually shows up more often. So this is A transpose y minus AX plus BX. Because B is self-adjoint. So is A. No, A isn't self-adjoint. B is. Okay? So that's the gradient. Is that correct? No, it's not the gradient. It's this is the gradient. I knew it looked funny. Okay? Now, so my point is, computing this gradient is expensive too. Now, so this thing here is going to look like this. Well, actually, it's quadratic in this particular case, but it won't always be quadratic, so it might look like this, okay? If it's a convex function, then it's got to be strictly increasing. We haven't said what a convex function is, but a convex function means that the second derivative is positive. So in a multidimensional case, the second derivative is a matrix rather than a scalar, okay? So what that means is that the matrix, called the Hessian, which is the second derivative. So if you take the gradient of f at a point is going to be a vector, right? But then if you take the gradient of the gradient, then that means each component of that vector you get a vector. So this thing's going to be a matrix. We'll call it H, say, right? It's easy enough to show that H of ij is equal to the partial derivative of f with respect to, say, xi, xj. That's just definitionally true, okay? But the derivative of a function smooth, if it's continuously differentiable, then you can exchange the order of the differentiation. So that means that h equals h transpose. It's got to be self-adjoint if everything's real valued. And then, so what that means is that it means that if you, well, okay, so the idea of a convex function is that, okay, the second derivative is positive, which means that, oh, I'm not even going to try to prove it. Okay, okay. It means that for all x, x transpose hx is greater than or equal to 0, okay? Which means that h is positive definite, or positive thank you. Positive semi-definite. Or the other way of putting it is non-negative definite. Okay? Okay, so the point is, when that happens, this thing will be monotone increasing, okay? Because any slice through this thing has to be a convex function in one variable. So this will be strictly increasing, so that point will be alpha star. So you could search for the point in which the derivative is 0. That's one way of doing it. Now to do that, you can do what they call binary search. So you, so if you have 2 points, we call it A and B, that you know bound the solution. So the gradient's greater than 0 on this side, and it's less than 0 on that side. Somewhere in between, you know it has to pass through 0 because it's a continuous function. This is continuous because that's continuously differentiable. This is a continuously differentiable function. Later we'll deal with functions which aren't always, they're not always quadratic, but they're usually continuously differentiable. And even if they're not continuously differentiable, well, yeah. Let's assume it's continuously differentiable. Sometimes it won't be, but we'll worry about that later. Tomorrow's another day, okay? So, do you know who said that? Well, actually, it wasn't a person. It was a character in a movie. Nobody knows? I can't worry about it now because tomorrow is another day. I'm shocked. Okay, you have to look it up. Okay, that's a homework assignment. So, shocking. Okay, so this is the solution, okay? It's the point at which this thing is minimum. So what we could do is we could do half interval search. We could find the point in between. Then it's either on one side or the other. And then you can keep, it's like, you know, you can look for the solution that way, right? But that still requires a lot of steps. In the quadratic case, this thing's a straight line when it's quadratic. So in the quadratic case, you can find the solution in closed form. But that's not going to usually be the case. But it'll be the case now, okay? So let's just review. Optimization usually consists of 2 steps. Find the direction, minimize with, do a line search, okay? With the quadratic case, doing the line search is closed form because the function is going to be quadratic, and you can always find the minimum of quadratic by just differentiating. You get a linear equation, okay? In one variable, because we're only trying to solve for alpha. Later, okay, but when it's not quadratic, things can get complicated. The other thing we're going to talk about is coordinate descent. Coordinate descent is sort of the mindlessly stupid approach, okay? In gradient descent, you're very clever, and you find it's like you're in this million-dimensional space, and you find an arrow, and you point. It's like you're a marks, you know, you're like an archer, okay? And you find this thing, okay, and you aim it exactly at the right point. Excuse me, that was chalk, I promise you. you aim it exactly at the right point, and then you fire your arrow, okay? And assuming you aimed it precisely, in just a few hours, it's like playing golf, okay? Where you want to kind of, like, I guess I'm not a golf player. Actually, I would have been a very good golf player, but when I hit the ball, it always goes in the wrong direction. But the thing is, it seems to me, in most golf course games, you want to get the ball in the hole in like 4 shots, right? Or something like that. So you want that first shot to be really close, maybe on the green, okay? That's what you want to do here. You want to line this arrow up very precisely and zoom, so you get really close. And then you do only a few iterations, but each iteration you put a lot of effort into really aiming precisely, okay? Because each of these iterations is expensive, so you don't want to do a lot of them. In coordinate descent, it's a different approach. There you're like, whatever, and you just like throw the ball randomly, okay? Well, not randomly. You like do some really dumb maneuver, okay? And then you pick a kind of a crazy direction. Actually, here's what you do. You take the pixels in the image, and you order the pixels randomly. And then you pick one of the pixels as the direction to move in. So it's almost a random direction. And then you update that pixel very quickly. Now the advantage of it, you'd say, well, that's really silly. The advantage of coordinate descent is that the updates are very cheap. But you have to do a lot of them. As a matter of fact, usually what happens is you consider one update of every pixel as a single update. That's really technically not correct, because in this framework, the update of one pixel is really counts as a single update. But you can do it so fast that you can do millions of these updates in the time it takes to do one of the very precise updates. So that's the name of the game. Now, what ends up happening is that there are variations on this. There's a thing called conjugate gradient, which I won't talk about a lot. In conjugate gradient, rather than, I haven't even talked about gradient descent. In gradient descent, the direction is the gradient. So actually, it's the negative gradient. In conjugate gradient, you try to fix it up by making it better, by taking the gradient and multiplying it by something which lines it up more precisely. And anybody here who's done deep learning knows all the deep learning methods are all based on more or less gradient descent, because they use back propagation to compute the gradient. But then what they do is they do a lot of kind of ad hoc little cute things, okay, to adjust the gradient with respect to some of the different components of the parameters, and also to adjust these kinds of step sizes and things. They almost never do a true line search. But so this is the overall framework, okay? Are there any questions about this? Because then I'll move on to the specific case of gradient descent, okay? Now what happens is that it turns out that different approaches to computing particularly to finding this direction, tend to give different characteristics to the convergence of the algorithm. And so the problem is that there isn't like a one-size-fits-all that works for every case. And that's why you need to know something about the optimization algorithms. One of the things that it used to be 10 years ago, when you asked a graduate student, what optimization, how did you do the optimization? They would say, I use MATLAB optimization toolbox, okay? And you'd go, okay. No, I mean, like, what actual algorithm did you use? Now what happens, you ask that question, and they go, I use an atom optimizer, okay? And then you go like this. So the point is that you want to actually understand what you're doing, okay? You want to have some understanding of what the algorithm is. You may not know every detail, but you at least want to have the basic ideas, okay? And the reason is that different algorithms have different characteristics. It'd be like, you know, a sports car is different than an SUV, is different than a school bus, okay? They serve different purposes. It's not that one's better or worse. They're good for different things, okay? So with gradient descent, Okay, what you do is D is equal to the negative gradient of f of x, okay? And I wrote out what the gradient was equal to. So it's equal to, so this is going to be y minus ax, A transpose minus bx, right? So then what happens is that x goes to, oh, by the way, this is called pseudocode. When I use an arrow, it means assignment, okay? Because if I write x equals x plus 1, that's a deeply disturbing concept, right? Because you can't, there's no x such that x equals x plus 1, right? So this isn't really equality, it's assignment. It's just that in Fortran and C, for historical reasons, they put an equal sign there, okay? Okay. So this becomes alpha times A transpose y minus AX minus BX. Okay? So, right. So this thing here is, did I do that correctly? X plus, this is going to be alpha times, I guess this is minus. Oh, no, I won't even. Let me just leave it like that. So this thing is the error. It's not really the error, but what it is the difference. Y is what you should have measured. I mean, Y is what you did measure. AX is what you should have measured if X is the solution. So the difference here is the error, the difference between what you did measure and what you think you should have measured. So you take that, and this A transpose is what I like to call back propagation. You back project it. So you apply the adjoint operator. You know, A transpose is like intimately related to, and in many cases is approximately equal to A inverse, okay? Or it does something similar. In any case, it maps the range to the domain as the inverse does, okay? So you do this, right? Now, what happens is that, okay, so that's gradient descent. So what happens is this. You can take, so this is xk plus 1 equals xk plus alpha times, this is going to be minus a xk minus b xk, and then this is plus alpha A transpose Y. Did I do that right? Okay. So this thing here is equal to I plus alpha, or minus alpha, times, is this correct? A plus B? This does not look right. Did I mess something up? Hold on. Did I mess something up? It looks like, I think I messed something up. Oh, yes, okay, right. Yes, thank you. This is not right. Alpha times A transpose, and minus B. Actually, in the notes I put a sigma squared in there. That was for, because I left the lambda out. The sigma squared was the noise variance. You'll read the notes, okay? Because I'm doing a slightly simpler case here, okay? So this is A transpose A. I'll put here plus sigma squared B. What was sigma squared? Sigma squared is the noise variance in the forward model. So this is the measurement noise variance. I know that was Maybe that was really wrong of me to insert this at this point because I just threw it in here, but at this point I felt like the intuition's more useful if I use it. How many people feel that me throwing the sigma in there is confusing? Okay. I'll leave the sigma out. The sigma is just if I had started this from the very beginning with lambda equals I times 1 over sigma squared. That's what I would have got. Sigma squared is the noise variance for the additive noise on the measurement. I should have included it from the beginning because it has the advantage that you then have the interpretation of understanding what it's doing. The reason is this. If there's a lot of noise in the measurement, then you don't trust the measurement, right? So the more you don't trust the measurement, the more you weight the prior model. Asymptotically, if the noise variance goes to infinity, you just ignore the data and you just give the person a smooth answer. Right? So the more, it's just like you keep, it's like as the noise goes up, you just keep dialing back the resolution and give them a smoother and smoother and smoother answer until all you've given them is something that's just smooth and uninformative, but it's the minimum mean-square error result, okay? I should have put it in from the beginning, but I just kind of want to put there so you can see how it depends on it. And it's derived in the notes, okay? So this thing is times xk, and then this is plus alpha A transpose times y. This is gradient descent. This is gradient descent, okay? So let's just revisit where we are. This is the gradient descent algorithm for solving the map estimate. So that's the iteration. Okay? Now, this is the point I want to make. And you're going to read the notes, right? And then we're also doing a thing tonight at 7? Okay. The point is this. So let me write this as, so if I define epsilon k, so if I take the limit as k goes to infinity, and I'm going to be optimistic here, then I'll have xk will converge to x hat map. X hat map. Okay? We're hoping gradient descent converges. If that happens, then I can define epsilon k equals I don't want to use the backwards definition. Is equal to xk minus x hat map. So epsilon k is the error in your current solution, right?